Monday, May 1st, 2023. Rainy, calm, cool. About 5:30, 17:30. From reading Einstein's Out of My Later Years, we pick up where it was left off in the chapter Physics and Reality, Section 3, the field concept. Now, the field is usually the idea that there are three space dimensions, and left, right, up, down, back, forth. These comprise the space that these three dimensions define by their extent and their measure and their regularity. And there's at least two kinds of regularity in space. There's the regularity of increment, that's usually called the measure, and the metric, that a meter stick or a yardstick, anywhere, a meter stick is the same length anywhere. And that x, y, and z, the usual names of these dimensions for a variable in x, a variable in y, and a variable in z, that lines are parametric, y equals mx plus b, to represent in y a relation to in x, that according to a straight line that's not a vertical line, at least, that has a parametric form, that there's similarly parametric forms for planes, and that there are various systems of functions which can define more or less any function as within a given range as a contrived enough polynomial, or as a sum of orthogonal functions or series thereof. Where in that differential geometry, there are some ideas of the immersions and submersions, where for some kinds of functions, they can actually be written in a finite series, that when you otherwise truncate what would be the infinite series, that for some systems of orthogonal functions, it's left off. Similarly, that for polynomials themselves, or some geometric shapes like the parabola, it's that, well, you can just write that as x squared. Y equals x squared, and it's a fait accompli, as it were. In finite terms, they're closed forms. Where an infinite series might be seen as a closed form, but in the sense that usually only what can be evaluated is some few terms, or when there's a linearization or small angle approach and there's any kind of approximation, that's any kind of error term, that they have non-zero and variable, these error terms, why it ends up in terms of numerical methods, approximations, that these are the kinds of notions that what make up for our field. Now, the field for mathematics, what a field means is an algebra with a closure of the integers to multiplication and division. So the integers might have addition and multiplication, and the positive only might only have addition and multiplication. Now, when you introduce the inverses of those, then you can get negative numbers. You can get, and you might consider also just like the positive numbers and their inverses only insofar as they're positive numbers. Whether or not it's closed on the operation generally reflects that when you close the arithmetic, the integers, to the inverses of addition, it results in negative numbers. And when you close multiplication with an inverse of multiplication to any member of what results as field, the field of the rational numbers, more or less, and pretty much, is that it results that this is what's called the field, is arithmetic of integers closed to division, so that it results that it are extended into the inverses of multiplication as for division, and defining these inverses, maintaining this regularity, another regularity sorts, that there's a sort of modular regularity. And so there's kind of a regularity of increment, and there's a regularity of modularity. And then when you consider that as utterly refined, then there's another sort of regularity, this regularity of dispersion, that on the number line, as it goes from 0 to infinity, as it were, that it's spread out, that there's some kind of constant distances that for the whole course Just as a simple matter of thinking in complementary duals, that these are the kinds of things there are, and that the infinity of these things has these units of it, the individua of otherwise what's called the linear continuum. And so sometimes when you think about infinity in integers, you might say, well, first of all, that's Archimedean means it has an infinitude of integers, and then Archimedean again means that there's no infinite one. That it's not infinite members in the infinite integers. That it still is, to be Archimedean, it's not finite. And then there's Duns Scotus, and Duns Scotus is somebody who kind of point to and say, okay, thanks Duns Scotus, you have an infinity in the numbers, because infinity is also related to the Godhead and the ultimate and this kind of thing, but also into the numbers, because by then there was at least a concept of this non-standard sort of analysis, which before there had always, of course, been non-standard analysis, but it was forbidden because it produced intractable or unsensible results. Yet there's methods of exhaustion since antiquity, and perfect forms and closed forms, and means to arrive at these numerical methods, and as well some forms of measuration where they arrived at least formulas expressing infinite products and infinite sums in terms of constants that are finite. And then that these infinite series and sequence of sums, we usually kind of refer to them, or I do, as kind of the telescoping, because when you think about an infinite series, it's in one dependent variable. And then the idea is that, well, it has to be the limit of the sums of the inverse powers of 2, which are half and half again, a quarter, half again, an eighth, dot, 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 which adds up to 1 for things like Zeno's paradoxes resolved, making Zeno's arguments for continuous motion in uniform time, which is a way to look at how those thought experiments both give a deconstructive account that you don't have to adopt necessarily, that what's the infinite adds up, then how you can and do, or that others may and do, thus that it's sensible to understand that the mathematics involves these infinite series which have finite sums. That the limit is a sum is after that the limit exists and is no different than the sum. And so then that gets into, then for Zeno, there's the idea of, well, if Zeno's arrow never starts as well as that it never stops, then it helps to see that it's splitting it, that if you have not just the end part, but each of the things in the middle, that it builds up an argument for why that in the way of a telescoping that it has to carry that recursion, that it's all the way divided. It's not the closure division, it's the closure of the divided. It's not the closure of the operation, it's as a result of the space, what happens when you define it the other way of the space. So that's a way to look at arithmetic, that addition is fundamentally separate from the division, and those are the two primary things that then make up this field of numbers. But everyone's familiar with the operations of arithmetic and the field of rational numbers, and the complete ordered field then of the real numbers. Because the rational numbers, well, dense, that in any given line segment that you can find infinitely many rational numbers as a simple exercise in multiplying out to a higher denominator and picking numbers in between, integers. There always exist numbers in between then if you multiply the denominator high enough. Similarly, the idea is that it's still not continuous because there exist irrational numbers, okay? And that the least upper bound axiom has to be satisfied. And so how that works out is that then there's a complete ordered field with least upper bound and measure 1.0 then defined. So after some axioms for arithmetic and algebras, and you can kind of see how it's sort of a definition to assign that there is the regular with or without the infinite for the Archimedean and the non-Archimedean, and then there's sort of a there's sort of a definition to implement either addition or multiplication in terms of each other, and why you don't want to multiply unnecessarily the fundamentals, because that's two different concepts. But one way to look at it is that there's a complementary dual that makes this fundamental if you think about division and its inverses and addition and its inverses as helping fill out arithmetic and the numbers. Though, of course, everybody learned division last, and that long division is last. So that's the field of mathematics, is the complete ordered field. And there's some result, for example, well, then the complex number is also a complete ordered field that is isomorphic to the real numbers, is what that the reals are, as a complete ordered field, are unique up to isomorphism in group theory, is a usual result out of algebra. Now you can equip -1 to 1, that interval, with operations, field operations, that provide that it satisfies the requirements of being a field. But these are, again, some of these non-standard functions. But it's just to be said that when we're talking about the uniqueness of the reals, the complete ordered field, up to isomorphism, then that doesn't include some of the otherwise these non-standard functions, doesn't include this non-Archimedean fields, doesn't include these other things that have been part of analysis since forever. Then that after Duns Scotus, for example, was kind of like, this is infinity. This is a place for infinity in the numbers at the top. And then there was Baruch Spinoza, who is excellent and kind of lonely, or of his time, one of the few people making this kind of statement in advance for the rationalists, that there's an integer continuum, that there's the infinite in it, and so that the integers form these individual of a continuum of the integer continuum with infinity. So that's the mathematics field. Then the physics field is space-time. It's a region of space, and so each point in space has an assignment as a number or a tuple of numbers, a vector in the vector space, say, is this Cartesian space, which is the multiple dimensions product of this real numbers, the field. So the mathematics field is a one-dimensional field. And then physics has one of each of those in each of 3 dimensions that define a lattice of the integers that's regular and regular and regular, defined by a rule. It's ruleal, and for this increment and modularity and dispersion. Then there's this Cartesian basis, the orthonormal, which makes it so that it defines a cube, which given the fact that it's the diagonal from point to point of the cube is the shortest distance that still fills out the full area of 1 by 1 by 1 in the vector space. And then what's all worked up to that is the notions of the squares of that in for example, boxes half the size, which always fall in, or this taking the square and then the root of that, about usual general ways to think about that a vector from any arbitrary origin could only be a certain distance away. And then if it's 1, then it kind of fits within these other things. So that is just about the multidimensional aspect of the field. So far it's an empty space with just a point everywhere, and each point is distinct, and each point can be represented by a tuple, and each point can be represented by a vector, which is a tuple, given the origin. So Euclidean space is just the space. A Cartesian space is an origin with an orthonormal vector basis, and then a space. So it defines everything by positive or negative from the origin. Left, right, up, down, back, forth. And then there's an empty space, and it's flat in the sense that it's not like curved in geometry, and it's not bent, parallel lines never meet, it's Euclidean, and even out to infinity, though according to the imaging and the optics of things, that everybody who's ever learned perspective in art class knows that there's a point at infinity. Everyone who's a photographer, knows that this is a thing in the imaging of things. Then has that there's another dimension for time. So this notion of the field in physics is universally parameterized by time, because over the course of this entire space-time, there's another coordinate setting. So because there's always a front and back and a left and right and a side to side in the space, Whereas in some notions of numbers, there's only like the unsigned or the magnitudes and not the inverses. Negative numbers don't exist in these models. That there's this three-dimensional space, then there's a ray of time or a dimension of time, and the time that goes back forever and the time that goes forward forever. And then there's basically whether the time that goes forward exists yet or not, that it's just a ray going backwards. And that it's just falling in to move that forward. That there's a ray of time from this origin of time. So every point in space has a point relative to any given origin. And then we can get into how that can be contrived, since we've been talking about Einstein and relativity, about the geodesy and the world lines and the curvature of that space with respect to how gravity's force is thus modeled, and the spatio and the space, as we've been just talking about with his deconstructive account of the fundamental classical laws of motion, or his attack on Newton, and that the notion of the time then is usually a dimension of time. So all of future time is assumed to exist in this projected ray the other way from the origin of space and time. That the origin of space and time is in the backward, that everything has already been done, and that's the way time goes, is time goes back forever, and then space goes out forever, and then that time goes on. And so that's just kind of an approach to what is a space-time manifold, and it's perfectly suitable for any of these other things, that then everything that goes forward in the formulaic is parameterized by time. And in the sense that that time symmetry has never been falsified in any experiment of physics. That it basically reflects at least one of the fundamental infinitely indivisible quantities, and that it's a universal. Okay. And that so is space everywhere, but at the same time, space is so objective, the origin is everywhere, and this kind of thing. So space-time, physics' field is the space and time, and then it has the contents of the space. So there's a book on the table, there's a clock on the table, there's a globe on the table, there's a shell on the table. And at each point, those points relative to an arbitrary origin, while they are not in motion linearly, then it reflects that at each one of those points in that space is a content. And so this content is basically what are called these field occupation numbers. So what is a field occupation number? It's that the field is just the coordinate space or the assignment of a value that reflects all these spatial relations and time relations. And then that the contents of the field are in numbers according to quantities of things. So the field occupation numbers are with respect to quantum properties, with respect to things like a body's mass or charge, with respect to others. And then the idea is that these fields, as any number of fields have a field of force, like gravity pulling on everything, and the strong nuclear force everywhere, which they say is very weak, and the electric fields, and then all these magnetic fields with regards to the interfaces with anything that exhibits magnetic effect or and where current flows, and that current flowing also makes for electric field, magnetic field. That all these different fields are superimposed, and so the field occupation numbers is a tuple, it's a vector of all these different numbers that reflect any kind of quantity or propensity or tendency. And then the idea is that the local is that one of these numbers is really associated only with the point. And the notion of these continuous transforms is things that are continuous in their bodies, in the surfaces, are so that reflects a continuous manifold. So this empty space-time is continuous manifold. It's smooth everywhere. You can assign things in it that describe as functions any kind of curvature. And similarly, when something's a continuous body or a continuous substance, or approach the same, or models as such, or motion in that, those end up also being part of the continuous manifold. But otherwise, for this vector field, has that any of these numbers for any of these fields, and they're independent. Any of these fields is abstractly independent until you have a unified field theory, which is like, well, there's one field and it's got one kind of special way to describe all the numbers. All these tendencies or propensities put together, like this fall gravity bit or something. And whether there is one or a grand unified field theory or like a grand complementary dual fundamental field theory making a unification, that then these field occupation numbers basically can also be themselves called vector fields. And so the vector field is basically this physics' field, and with its space and its vector space, and then its fields on that, everywhere omnipresent in the vector space, and then those notions of the field occupation numbers. And then for the quantum theory, then it's like at the atomic level, and anywhere the quantum behavior emerges, it's like so. And then for these continuum mechanics, it's like so. And for all these things, it's like so. That then the total field is like, well, the field of all the things, the total grand unified theory, the theory of everything, has to be this kind of total field theory. Science has established thus far that space-time is flat. Which speaks here particularly to this read of Einstein, where this is an Einstein's flat universe field theory, and that it's a gauge theory, that anything that involves a highly nonlinear just reflects that there's a gauge that affects the metric. And so this basically has that there are no closed time-like curves, but space-like curves can have warps. Because then there's the extra local. Then anything that's just a field occupation number as well would have a structure that is whatever its extent. So that's just bodies, classical bodies, and as well any kind of system, an inertial system, as Einstein puts it. Anything that fits in the field occupation number formalism is this kind of thing, has that the field occupation number formalism is as grainy as it can get, down to the levels of atoms, down to the level of quantum, down to the level of the Max Planck's length and mass and time, and down to the level of the superstrings, way beneath that is just like, is if you need more continuous, then make more continuous, because it's just like in the real numbers field, if you only had a finite smallest element, though there's no smallest standard element in the standard real numbers, of course, there would be a smaller one, because it's closed to division, you can divide it by 2. Then until you get to something like an Aristotle's continuum, which has an infinity of these infinitesimals between them, that then you haven't really approached that as the objects in the universe. This is the idea is that the points, atoms are actually infinitely small, and there are infinitely many of them in a mole. And we just have to deal with how they have finite extent and finite ratios, because it works out in the classical that stoichiometric, and of course that's great, and there's nothing wrong with it. It's just not a full, complete picture, and so only at this quantum mechanics and the mechanics of space-time do you have to really care. But then it still works out that it's a continuous manifold, and that it works out that empirically and according to what resources are, it can only be so grainy, and before there's not a fine enough measure. You can't read the difference between a billionth and a trillionth kind of a thing, if at all. And feeler gauge type thing, That here, it's the field is a field. So that's physics' field. And here's Einstein, section 3, the field concept. In explaining optical and electrical phenomena, Newton's mechanics has been far less successful than it had been in the field cited above. The word field is overloaded, the classical action, classical mechanics. So there's subfields of mathematics, but sometimes there are superfields of mathematics, like when the generalized really is the particular with respect to another thing. So there's always this inverse and complementary duals to figure out in these contexts of these things. It is true that Newton tried to reduce light to the motion of material points in his corpuscular theory of light. Later on, however, as the phenomena of polarization, diffraction, and interference of light forced upon his theory more and more unnatural modifications, Huygens' undulation theory of light prevailed. Probably this theory owes its origin essentially to the phenomena of crystallographic optics and to the theory of sound, which is then already elaborated to a certain degree. It must be admitted that Huygens' theory also is based in the first instance upon classical mechanics, but the all-penetrating ether had to be assumed as the carrier of the waves, and the structure of the ether formed from material points could not be explained by any known phenomenon. One can never get a clear picture of the interior forces governing the ether, nor the forces acting between the ether and the ponderable matter. The foundations of this theory remain, therefore, eternally in the dark. The true basis was a partial differential equation, the reduction of which to mechanical elements remained always problematic. So here he's referring to several things. One, for example, is that ether theory isn't a thing for lots of people because it assumes a background of sorts for that is space. But at the same time, Einstein just defined how his space is associated with these things, and so even if it's not an ether, it is at least a geometric milieu for same. So space-time is not an ether. It does not have any drag in it. It's a vacuum, meaning it's entirely empty. But then whether it's a direct positronic C or that there's not frame dragging or lens slurring effect, these are things that happen to be part of our aspects of being in the sun's frame and being in the galaxy's frame, with respect to that all the coordinates on this table have stayed zero distance with respect to their other ones on the table, but the entire Earth has been spinning around through an entire galaxy while doing so. That its differences are essentially nil with respect to the rest on the table. Then here, with regards to the undulation of light and what's the ponderable, there's that these wave mechanics are somewhat imponderable, because it's like, you mean that a wave is really like, it's kind of like when the electron theory gets to that, well, it's probabilistically possible that an electron of the clock is actually all the way up Mars right now and then just came back because it's probabilistic and it has a long tail. It goes up to infinity. Or anything to do with the spooky action at a distance, anything that's a non-local. Now here, for special relativity, Einstein has already given us, for his theories, this action of the local on that part of the space he's attached to every point in space-time, this field, and here he's filling us in why then he'll be able to put back together the pieces that he wants, whereas otherwise his original awesome papers from the Annus Mirabilis about the optoelectronic effect and this kind of thing, which are basically about the photon, because of electron physics being so utterly great in terms of establishing fundamental physical constants in the regime of the time, the energy experiment, configuration experiment, that today we know are about running constants and the ultimately vanishing or infinitesimals or infinite, that Einstein is declaring these things as like so. Not that they're to be brought in and made things that otherwise, without the proper deconstructive and reconstructive count, made incongruous or inconsistent in other theories, but only in a sort of correct reconstructionist after deconstructionist account is there to be this Einstein's field concept. All right. On he goes. For the theoretical conception of electric and magnetic phenomena, one introduced, again, masses of a special kind. And between these masses, one assumed the existence of forces acting at a distance, similar to Newton's gravitational forces. This special kind of matter, however, appeared to be lacking in the fundamental property of inertia. The forces acting between these masses and the ponderable matter remained obscure. Well, this is the notion, again, of these quantities that really live in the fields of potential. The fields are the classical fields usually. That's when you attach, for example, classical Newton's field to an empty space-time. It's all by itself. But if the idea is that otherwise all these potential fields add up, and then it just happens to also result in the middle for contrived or simple situations, the same in the middle, that's about how the middle is, or these classical fields result being an approximation. And then when that has certain particular nonlinear results that show up and what make the dynamics, that's just one system of potential fields that add up to this. That the potential is our abstract, utterly deconstructed, utterly reconstructive. And so these actions in the magnetic fields, he's like, well, the Meissner effect has made this ingot really, really weighty, yet its electromotive force reaction is highly increased. Or these kinds of things with respect to the effects in the magnetic and the establishment of standing waves. And the extra local are that there's no model of this because in our classical model of it, it's not a thing. But there's this extra classical model, superclassical models, that is just totally naturally a thing. That's all it is. And so when one is equipped in the intuition for the context, these sorts of, first to have a very firm grasp of the classical notions, because again, in the mathematical and in many ways the linear and the impulse and the regular and rulio, especially from the small numbers, is absolute. That also there's this other replete absolute of the infinity, and that this makes for these superclassical numbers. So after having a very firm and intuitive and classical grasp is to have this intuitive notion unavailable to our senses except to our sense of reason and our analytical deconstructive account of the coherency of the totality of these things, how it can come back together. And then inertia, momentum are kind of poorly defined in classical mechanics. That was rather kind of a Parthian, but I feel it. This special kind of matter, however, appeared to be lacking in the fundamental property of inertia, and the forces acting between these masses and the ponderable matter remained obscure. To these difficulties, there had to be added the polar character of these kinds of matter, which did not fit into the scheme of classical mechanics. Again, this is that, well, a standing wave actually is oscillating at at some arbitrarily high oscillations per second, and then by the time it's like a balloon or a tire would get a hole in it and would kind of air out of there. And one of these, if it ends up collecting to coalesce to a point, then everywhere else it pretty much disperses at once. It's only held together, the whole thing, that it's instead of like a chain having a weakest link or a weave having a rip or tear, it's that they're infinitely tough, but if you actually, and it's like a mesh or a mail, but if you actually get through it, then the whole thing just vanishes or collates to it. This is the basic idea of the pilot wave and the ghost wave, the Bohm de Broglie particle wave, that for the particle's extent and duration, that it's just the opposite of classical. And it's infinite, where this stuff is infinite, that it still has the same models of tension as to its mechanism. And that's real, because then everything is a model of potential, including the objects themselves. An object in the context is everything that it is not. And it's the same context when that's the opposite. To these difficulties, the basis of the theory became still more unsatisfactory when electrodynamic phenomena became known, notwithstanding the fact that these phenomena brought the physicists to the explanation of magnetic phenomena through electrodynamic phenomena, and this way made the assumption of magnetic masses superfluous. There were developed higher order classical theories. There became more and more specific things in the fields that's among the reason why magnetics already has 20 or 30 different potential fields in magnetism, because it's used to develop all these contrived things. They're not classical fields. They're not necessarily the true fall potential field. It's kind of like Higgs's field is not a field, it's just an interface effect. And so what those are effects of the interfaces, and they define transition effects, and otherwise what would be symmetry and conservation laws, these transition laws about the continuity. So they're not, some of these are real potential fields. And for any classical field, it's like, here's a potential field, it adds up to it, but it's abstractly the opposite. There is one. And then for this something like these not a classical fields, and actually just a surface definition or behavior, or it's a vector field and it's 1.0 everywhere, and we brush it or something like that. Those are different things. They're methods in the milieu. Brought the physicist to this progress had indeed to be paid for by increasing the complexity of the forces of interaction, which had to be assumed as existing between electrical masses in motion. We can talk about that nonlinear electromechanical effects and applications of Mogan, and how he's really helped bring that down to a single parameterization. What's going on? The escape from this unsatisfactory situation by the electric field theory of Faraday and Maxwell represents probably the most profound transformation which has been experienced by the foundations of physics since Newton's time. This is that the electric field theory defines the magnetic field theory, at least, and so that brings a lot of its stuff together. But it's still this other stuff that still exists. So he's kind of talking about the time before, and then framing the time after that in terms of that, setting people up in case they didn't know about it already, that they wouldn't later look at him as ignorant, because he certainly should and would have been aware of this at the time. Again, it has been a step in the direction of constructive speculation, which has increased the distance between the foundation of the theory and what can be experienced by means of our five senses. See, then it seems we need to add just this object sense and to figure out what are the requirements of these objects, like the true potential or the context, that make it so for an object sense that the intuition arrives existing for the superclassical as relating always to our classical models, always in the same way. That, well, flux is always going out and it's tachyonic, or to complement our notion of flow and it's bradyonic, or these kinds of things with regards to it's like infinite surface tension, but then it breaks everywhere at once. Well, then you can define the classical, and that is one of those with zero, or something like that, to make it clear that there are these complementary duals in the space for the points, that Einstein's material points being so key from this previous section is the same that the material space is so key. And here the field, that they're complementary duals. And that means complementary as of the remaining part, and the dual is the secondary or the twin compared to the complementary, which means as of a pleasing complement, or that which appreciates. And the duel, which is a formal argument in various formal ways. The complementary dual is this notion of a deconstructive account of anything must result that our total unified field theory is a total unified field theory. It's reconstructivism. It is constructivism. So anyways, going on here, again has been a step in the direction of constructive speculation that speaks to his definitions, Einstein's definitions of what the desiderata and requirements of theory, the constructive, which has increased the distance between the foundation of a theory and what can be experienced by means of our five senses. So he's saying whatever is the foundation of our theory and what's real and not available to our five senses is this part, the foundation. The existence of the field manifests itself, indeed, only when electrically charged bodies are introduced into it. I don't know if I can't really say this, so it may be for Maxwell's field. The differential equations of Maxwell connect the spatial and temporal differential coefficients of the electric and magnetic fields. Here these are Maxwell's fields. And these are the only ones he's mentioned so far, so we kind of have to assume that that's all he means. The electric masses are nothing more than places of non-disappearing divergency of the electric field. Light waves appear as undulatory electromagnetic field processes in space. Light has no charge. It has energy. It's according to its intensity and frequency and wavelength, but it has no electrical charge. And